Yep, I started recording it.
All right, cool. So hello, everyone. Welcome to the HKN Depths Workshop. Thank you all so much for coming, both the speakers and attendees. So my name is Shashank. I'm the ECE Tech Chair currently of HKN. So, so this is what the agenda is going to look like, if you can see my screen. So I'll first go over the general core classes you had to take in electrical engineering, and then I'll later have all the depth speakers talk about each depth. So my plan is to have, like for each depth, I'll have each speaker go over, what the depth is about, what opportunities you get, and then at the end, like for the last 5 minutes, we'll have a Q&A session between the participants. So get started. So this is gonna be the list of classes that you had to take initially for electrical engineering. So as you can see, there are a lot of math and physics courses that you had to take. Most of them are in fact a prerequisite for the first real ECE class, which is 35. You also had to take ECE 15, 25, and 17. But 35 is really what lays the foundation for the future classes that you're gonna take. And also, each class is color-coded in different years. This is recommended based on the 4-year plan, but you can always do it early if you want. However, it is recommended that you do it early. And also because of all the prerequisites thing, it's highly recommended that you plan out everything beforehand, just so that you don't find out the prerequisites and all that and have that become an obstacle. So this is the list of lower division ECE classes that you had to take. So like I said before, this is the recommended years that you'd be taking it, but you can always take it sooner. And so really it's 35, 45, 65 specifically. Like I recommend that you take it as soon as possible, because for the future upper division classes, you'd need these as prerequisites. These are the breadth courses that you had to take. So basically this really based on what topics you're interested in, you could go on to specialize in different depths. So, this is where you're going to be learning about different kinds of fields and courses and all that. So go on to the next. And also just to mention, based on what depth you want to take in the future, you may or may not need some of the breadth courses. So you may want to keep that in mind. So these are the list of depths that ECE currently offers for electrical engineering. You can choose from about 8 depths. So as you can see in the green and yellow boxes, those are the breadth courses that you would be taking initially, and then the gray, the courses highlighted in gray would represent the specialization that, like the courses that you would be the depth courses that you're going to be taking. And also keep in mind that based on what depth courses you're taking, you'll be having the breadth courses as prerequisites, which is why you'd be taking that earlier. So we'll introduce the first speaker. So Bert would be doing devices and materials. So Bert, if you want to start.
Yeah, sure. Okay. Hi, everybody. My name is Albert Heath. I'm an alumnus of UCSD's ECE Department. Sorry, not too bad. I got my bachelor's in 2016, and I got my master's in 2018 in the field of electronic devices and materials. I spent a lot of time studying the physics of semiconductor materials, and so I have a rather deep understanding of the basic semiconductor devices used in everyday circuits, including the stuff that you see in ECE 65 and 102. To start off, the devices and materials depth is a deep dive into the physics behind your nonlinear devices, where in ECE 35 and somewhat in ECE 100, all of your circuits are linear, the world isn't quite that simple. And so we dive into the deeper mechanics behind these nonlinear devices to have some more interesting results coming out of them. And you've seen this in your ECE65 classes, your ECE65 labs, like your clipper circuits with your diodes, and also your amplifier circuits with BJTs and MOSFETs. This depth, this devices and materials depth, is primarily physics-based, but there is a lot of crossover with other disciplines, including nanoengineering, chemical engineering, and mechanical engineering. In addition, there are some material science and some amount of photonics used in studying this subject, since semiconductor devices are basically just made out of material electronics. And photonics is also a very related field to electronics. On the applied side of things, you also get to learn about the fabrication process and the process engineering that it takes to design and develop chips in your CPUs, for example. The depth also includes a lab class where you actually fabricate a diode and transistors, and you get to study them, you get to apply voltages and currents on them, and then you get to analyze their performance, etc. All that said, this depth is rather intense in its subject matter. Graduate school education is usually necessary to be able to make contributions to this field, but there do exist jobs that don't require graduate education to be able to make a living. For example, there are many companies that make lab equipment, and having a foundational knowledge of the process engineering behind making these chips can be helpful in developing those lab equipment. So let's go ahead and move on to the next screen. Right, okay, there we are. The classes in the devices and materials depth funnel off of the breadth courses of ECE 103 and ECE 107. ECE 103 is an introductory class to the fundamental principles behind nonlinear semiconductor electronics, whereas ECE 107 is a class in electricity and magnetism, which is important when you get into the interplay between electronics and photonics, or rather the electron and the photon. ECE 107 also teaches you about RF circuits, which is another application of semiconductor materials, since specialized materials and specialized chips and specialized transistors are needed when you push into higher frequency communication circuits. With regards to the actual classes in the depth, ECE 135A and B are classes that go in depth into semiconductor physics. You'll study some more of the fundamental physics, including solid-state physics and quantum mechanics in semiconductor physics, before you move on to explore the actual physics and math used in analyzing your transistors, your diodes, and so on. You also get to study some solar panels, which, by the way, are also made out of semiconductor materials. There's also a lab class, ECE 136L, that takes you through the entire fabrication process for some of your devices, like the diode and the MOSFET. It also teaches you general fabrication engineering or process engineering principles along the way. ECE 183 is a class in optical electronics, which is a functional class discussing the photonics application of semiconductor materials. ECE 183 is also a class in the photonics track, where ECE 181 through 185 all discuss a different topic of photonics, but in particular 183 is most related to semiconductors, because in this class you design a simple laser device while studying the physics of photonics and electronics, combining them together using semiconductor materials. I'm going to go on to the next screen here. All right, and so the job opportunities that you get out of having a depth in devices and materials, it's not the usual stuff that you would normally get out of being an electrical engineer. Most people think you might be a DSP engineer or circuits engineer, but a lot of job opportunities you get out of studying these devices and these materials and all this physics, it allows you a unique opportunity to work on some of the things most electrical engineers never really worked with before. In particular, because you know process engineering and because you understand some fundamentals about the fabrication of your integrated chips, you get to work in companies like Taiwan Semiconductor, you get to work at Intel, and you get to work on global foundries. You might be able to work in these foundries where you are directly involved in the processing and the fabrication of the chips that go into your CPU. In addition, because you have such a strong foundation in physics, you can also find yourself working with magnetic materials. There's been some I wonder if the word is humdrum, but there's been a lot of hype, at least when I was in school, about being able to use magnetic materials and spintronics to make circuits as opposed to making electronic circuits. And we also have a lab, an institution on campus called CMRR. It used to stand for Center for Magnetic Recording and something else, but now it's the Center for Memory Recording and Research. In addition, you also have the companies like Hitachi, Toshiba, and Samsung that work in magnetic materials and hard drives. There are also several national laboratories that you can potentially find yourself working at, just because of the fact that you are more well-versed in physics and you're able to understand some of the deeper principles behind our electronic circuits, as opposed to a lot of circuits engineers who just kind of monkey around on their circuit simulator to be able to produce their results. Oh, JPL is also included on this list. They also do some research in semiconductor technologies. And lastly, you also have application in RF circuits, because you have an understanding of how things work when you get into increasingly higher frequencies. Like you study in ECE 107, you can't use simple KVL and KCL to solve your circuits. You have to start using transmission line theory to solve your higher frequency circuits, your RF circuits. And those sorts of circuits also require different kinds of transistors and different materials. For example, amplifiers might use a particular kind of 3-5 semiconductor material, whereas in CPUs and computational circuits, you would use more silicon-based semiconductor materials for your MOSFETs. And if you study, if you take ECE 135 and 136L, you'll be able to understand why we use different semiconductor materials for different applications. And with RF circuits being a popular field for engineers, for electrical engineers, it's good to have that sort of background. And of course, you get to work at Qualcomm and Broadcom, etc. Going to move on to the next slide here.
Are you not able to control the screen?
It says I'm not able to control. Well, anyway, yeah.
Okay.
So research areas. I mentioned CMRR earlier. If you happen to be able to work with the professors in CMRR, if you actually happen to know Eric Fullerton, he is the director of CMRR, and there's a lot of connections to industry there. You also get to do research on solar cells. If solar cells are what floats your boat, green energy is what floats your boat, this is also a good opportunity to understand the physics behind solar cells and what sort of semiconductor materials you would use for solar cells, which also, by the way, has applications in space. And that's cool. You get to work in space. You also have the opportunity to work in the field of memory. You get to work in high power gain electronics. You also get to work with some interesting novel fields in, bioelectronics, or electronics that interface with the human body. You have electron-neural interfaces. For example, you also have flexible and organic electronics. And there's also been a push from the ECE department to develop more research in that field, including Professor Ying, Sina Ying, and if I remember correctly, Professor Hall also has some research fronts in the field of organic and flexible electronics. In addition, you also have the usual laser applications, and semiconductors are also a material that you can use to make lasers out of. And of course, you'll have transistors and Moore's law, which I'm sure you all heard of transistors and Moore's law, and you all are also probably curious about the answer to Moore's law because it's getting harder and harder to actually double the amount of chips that we put in our CPUs. So if you study semiconductor materials and you study these different transistors and novel transistor geometries, you can also be included in the effort to find a way around maintaining Moore's law as time progresses. So let's move on to the next slide. Yeah, I don't actually have control.
Just a second. Okay.
Ooh, yeah.
Are you able to control
Yeah,
it?
I got it now.
Oh.
I think. Because I'm controlling your screen, but I'm not sure if I'm actually, let's see if I can do that. There you go. Okay. So here is a diagram kind of depicting the fabrication process of a transistor. It's kind of involved, and there's a lot of processes, and there's a lot of chemistry and a lot of chemical engineering that's involved to be able to make it this far. But y'all have to understand that this is how we got all of our technology. This is, well, I can't say that this is how it started in the beginning 50, 60 years ago, because I don't believe that the first BJT was fabricated this way. But this is definitely this is definitely one of the most widely used processes to make our CPU chips. At number one, we start off with our silicon crystal. It starts off as this ingot, which is this really, really long piece of pure silicon, from which you actually make cuts. You make the cuts on that silicon wafer. I'm sorry, you make cuts on that silicon crystal on the ingot to make a polished wafer. And on that polished wafer, you do a number of process engineering, including making a silicon dioxide layer on top of it. Then you use some lights. You use a light and some lens and a pattern to make the particular CPU chip design that you want on there. And then you go through some photoresist, you go through some burning, you go through some dissolving, some etching, some stripping, all through 4, 5, 6, and 7, and even 8, doing all of these all of this processing just to be able to make your CPU. And you know, all of your foundries, they do this at a massive scale. And you know, from this massive process, you get your CPU chips that you can put in your computer, and it does processes for you. It does computations for you. Not only that, there's also other processes used for solar cells. I'm sure that that's a different process, different from what you would put in CPU. And you know, there's just so much to have to understand before you can even get CPU getting a NOR gate or an AND gate, right? All right, I'm gonna move on to the last slide that I have here. Here we have some pictures of the Nano 3 clean room, and this is a lab space that a lot of our PhD students and a lot of our professors use. And there's just all this equipment, there's all of these people wearing masks, not just because it's coronavirus, but because if you actually breathe on your chip, you have a chance of contaminating your samples, and that affects the electrical properties of your samples. You also have all this lab equipment. A lot of it is electrical because you're making electronics, and you're trying to verify that your electronics work as intended or works as research. Then you also have a lot of other lab equipment that involves like microscopes and, you know, masking and lights, and also stuff that works in these vacuum chambers, because there's definitely a lot of processing techniques that you know, manipulates, or rather utilizes our understanding of physics to be able to apply these processes on the chips themselves. Anyway, so this concludes the depth of semiconductor devices and materials, I think I can just revert back over. I can give control back over to Sashang.
Yeah. Do you guys have any questions for Bert?
Any questions for now?
Yeah, Bert, could you talk more about your experiences in industry and potentially compare that to any experiences you might have had in academia?
So this is where it gets a little bit embarrassing because currently I work in a job that doesn't really utilize all of this understanding of semiconductor devices and materials. But there's been a number of my colleagues who come up to me and ask me questions on, oh yeah, so do you know why we use this particular type of semiconductor, or can you explain how like electronics work in general? And I've actually thought about giving a sort of seminar to my colleagues at my workplace for those who didn't really understand electronics, a seminar on how all that stuff works. The reason being is that I'm a master in semiconductor devices and materials. I'm a master in material electronics. And so we interface with electronics and electricity and all these things every day, but we don't really understand why or how it works. We almost take it for granted. That's actually one of the major reasons why I wanted to pursue this depth, is so that I could have a better understanding of all this stuff and not have to, be worried at night about like, oh, I actually have no idea what happened in the lab. I do have some research experience in semiconductors. I did a half a year abroad in Japan, just doing full-time research for a professor there at Osaka University, and it's a lot of fun when you are able to apply not just the knowledge of one field of electrical engineering. You get to put it all together, and you get to understand how things work and how things can be improved, and you can start developing new technologies. Like, instead of having circuits made from electronics, you can have circuits made from magnetics, or even from photonics, you can have light circuits. So it's a long-winded answer of saying I can't really relate what I'm doing now in industry because I don't work in that field with what I have learned in academia. But again, it helps a lot in your background in understanding how things work. And I also do have friends who are working in industry on lab equipment that requires an understanding of the photonics and the physics behind electrical engineering. And, it helps a lot.
Thanks, Bert.
Mm-hmm. Anybody else? All right, well, I mean, if nothing else, then I give control back to Lashai.
All right. So we'll move on to the next step, which is communication systems, which Neil will be talking about. So, Neil, are you there online?
Yeah, I'm good.
All right, cool.
All right. So, hey everyone. My name is Neil, and I'm a fourth year doing electrical engineering with specializations in both communication systems and signal processing. There's a lot of overlap between these two fields, and I've taken the core coursework in both of them. So if you have any questions about what that's like, you can let me know after the presentation or message me directly. So at a high level, some topics we study in communication systems are transceiver architectures, information theory, coding theory, and network theory. And I'll discuss that in a little more detail, but for now, the breadth courses that you should be thinking about that would indicate an interest in these are signals, probability, and statistics. That means that you'll want to consider how you like the material in ECE 101 and 109. All right, so the fundamental problem in communication systems is to send information across a noisy channel. And solving this problem is relevant in technologies ranging from wireless networking to cellular communications and military secure communications. Here we have some examples of these: Wi-Fi, 4G, LTE, 5G, etc. And turns out that 5G does not cause coronavirus, so that's not really something we study in this depth. As always, there are trade-offs in communication systems. On one hand, there are real challenges to sending information. Signals that we want to send are corrupted by noise. If we're using a transmission medium like copper cable or optical fiber, signal power may be reflected back to the source instead of reaching the destination. And in general, we have to deal with attenuation and minimize our likelihood of error in spite of this. So that's one constraint. On the other hand, we need to minimize the resources we're using: bandwidth, power, and cost. So the channel impairments that I talked about earlier and these design constraints are conflicting goals, and our job is to min-max and optimize our solution. And in order to do that, we implement clever modulation and detection schemes to send and receive information, as well as error correcting codes to make our communications more robust. All right, if you can see the slide, this is a block diagram of an OFDM system, which stands for orthogonal frequency division multiplexing. This system is a useful study because it ties together a lot of concepts that you'll be studying in a communications depth. For example, modulation, coding, and converting between analog and digital domains. And in particular, I want to touch on modulation and coding a little bit because they're a big chunk of the comms depth coursework. So modulation is essentially taking a carrier signal, like a sine wave, and varying its properties to embed information. And one example of this is amplitude shift keying, where the transmitted waveform is high when we want to send a 1 and low when we want to send a 0. And all of this is pretty low level, this modulation stuff, because we're looking at the actual waveform that's physically transmitted across the channel. On the other hand, we have coding, which is more of a high-level field. Coding is representing and compressing source information. Suppose I want to send you only letters A and B, and we want to think about how I would send that to you in binary. So I would say, okay, if I want to send you an A, I'll send you a 0 and B 1. Now think about what I would do if I wanted to send you a full alphabet. And we have to realize that every letter is sent with a different frequency. You know, some letters are more common than others. And on top of that, if I send you some letter, that gives you information about the letters I'm going to send following it. For example, if I send you a Q, there's a pretty good chance that I'm going to send you a U after that. So all of these statistics and probabilities determine how we begin developing a code book for the alphabet. You know, the codes for letters that you send often, maybe E, should be shorter than the code for a letter that you don't send very often. For example, Z. All right, next slide. So these are the courses you'd be taking for a comm systems depth. First, looking at ECE 153. This is essentially an extension of 109, which covers probability and statistics. This is looking at random variables over time, which is the random process. And different properties and different random processes. In 155 and 159, you implement a lot of the probability and random processes that you learn in 109 and 153. And these classes cover modulation and coding schemes, which I mentioned a little earlier. And 158A, that relies more on 109, and it briefly covers queuing theory, different network layers, and routing algorithms to traverse a network. All right, so let's look at what comes next. There's a strong need for communication systems engineers, both in the commercial and defense spaces. Often you'll be working with wireless technologies and or satellite communications, and here are some examples of companies that do a lot of comm systems work. Personally, my experience is almost exclusively in defense. I was previously a year-round intern with Northrop Grumman in their aeronautics sector, and I recently signed full-time with them in Space Park. I had a great experience with them, and if you'd like to know more, feel free to ask questions or message me after the event. All right, here's a variety of topics you can expect to cover in graduate courses. We briefly touch on some of these in the undergraduate curriculum, but all of it is fairly superficial. There's a limited time that we have. So just to wrap up, communication systems is a deep field, and in my opinion, taking a handful of depth courses in undergrad will only scratch the surface. So from my perspective, I'm a senior. You simply can't learn a lot of the comms in the limited time frame you have in undergrad. There are only 4 courses, and I don't think that's enough to learn communication systems. So if you end up doing communication systems, I would highly recommend doing grad school in order to learn the field more deeply. And that concludes it. Any questions? All right, if there are any questions for now, I'll pass control back to Sashank. If you do think of something later, feel free to message me personally, and I'll be happy to answer.
So we could move on to the next depth, which is circuits and systems, which Austin would go.
Oh.
Yeah.
Cool. All right. Do I have control right now?
Let me give you control really quickly. Okay. Are you able to control it now?
Let's see. I don't think so. Oh, wait. Yeah, I think it's good now. It's just a bit laggy. Okay, cool. Great. So, hi, I'm Austin. I am currently a graduate student in ISRC, and in my undergrad, I actually was a triple depth. I completed DSP, circuits, and machine learning. And so circuits is the depth I was primarily interested in when I came to undergrad, but later on I chose machine learning. However, the reason why I want to do circuits is because it is one of the most, they say, prestigious fields within ECE. Because when you think of electrical engineer, you first of all think of circuits like ICs or PCBs, right? Both of which are devices that we use to control all our technology. And so within the circuits depth, there are 4 core classes: ECE 163, 164, 165, and 166. So I first want to talk about 164 through 66 because those I feel are the most representative of the actual depth. So 164 is pretty much an extension to 102, in which it's just more, what's called MOSes and transistor devices, essentially. You figure out new configurations for them and design amplifiers and learn how to analyze amplifier circuits more efficiently. There's less focus on how to determine each specific voltage, whereas you determine the functionality of all the components together in lump sums. And so 164, I feel, is one of the more, challenging courses within ECE or within the circuit staff, just because of the fact that it does extend off 102, but you feel like it should be a continuity. Like it seems like a direct continuity at first. However, it branches off quite steeply and it races towards being something completely different. And so within analog IC design, you actually get to work in the labs, or in one of the lab projects, you get to actually design your own circuit. So you have to find the optimal points for width and length of a transistor such that you can achieve a desired amplifier. And so 164, I feel, is probably the course that you should take to decide whether you want to stick with the depth or not. 165, however, is completely different from the rest of the courses, or from 164, in that it focuses on digital ICs, which it still relies on MOSFETs and transistor circuits. However, you'll see that you'll use a lot less of what you learn from 164. In fact, almost none of it applies to 165. You actually mostly focus on digital logic from ECE 25. And so that's the one, so this is the one class where ECE 25 is relevant as a, as a prereq. So in 165, you design logic gates at transistor levels, such as AND gate or NAND gates, NOR gates, inverters, etc., and move on to more impressive logic and much faster logic. The whole point of the class is to learn how to optimize this digital logic to make it run as fast as possible. And in 166, once again, it's another very different class from the other two, in that now you're working on less ideal circuits. In fact, you dive deep into the non-ideality of physical circuits, in that now your wires are no longer just perfect ideal wires. You have actual you have the electrical wave behavior to account for. So ECE 166 covers RF circuits, your radio frequency circuits, which are really high frequency, and so you'll now have to deal with the wave behavior in your circuit models. So what you'll see is that each of the wires will behave as transmission lines, and with it, their own set of non-idealities, in which you'll learn how to analyze and work with to improve your circuits. In fact, this non-ideality is something we can exploit to achieve quite drastic dynamic range, and which lets us achieve power levels so low that we can actually measure the background noise of space, which is really cool. Now, back to 163. The reason why I say that this class is very unlike the rest is because it's less a circuits class and more so a combination of controls and actually DSP. Because one thing I found myself constantly, finding an advantage in was the fact that I was a combination of machine learning, DSP, and circuits. In 163, most of the students have very little knowledge of controls beyond ECE 100. And so when they reach 163, they feel overwhelmed by the amount that they have to know and the level of depth that we go into actual signal processing as well. For example, the topic of PLLs, which is phase lock loops, is never covered in any of the breadth courses, yet it's almost assumed to be common knowledge within this course. This is how it was when I took it, but in recent years, apparently Professor Shui has done a good job of toning down the necessity of DSP and controls to only require levels from ECE 101 and 100, which is really good, but at the same time, you lose a bit of value. Because this class was sort of a gateway into 264, which does focus more so on the control aspect of circuits. And so moving on to that, the graduate level courses are the 264 series and 265 series, in which you discuss more so on the non-idealities within your circuits, but you focus more on like actual architectures and systems, such that you can achieve a functional design for something like an amplifier or even a receiver. And so one example is the idea of a radio receiver. This is a topic that's quite or somewhat covered in 166, but much better covered in the graduate level courses. So in your radio receiver, your radio frequency signal is input into the receiver and then processed through a filter. Then once it's filtered, we apply an amplifier. And so the thing that that's very different about RF circuits versus what you may have learned from 35 up to 102 is that all your wires behave as transmission lines, and we can exploit that to achieve radical gains and make the signal much, much larger than we would normally be able to. At the same time, we have more ways to deal with noise as well, which is quite impressive. And so the RF filter and RF amplifier, unfortunately, you don't get to really learn about those in the undergraduate level courses, but it's something to look forward to in grad courses. Same for the mixer. The mixer is actually quite an interesting device. So it's a critical stage of the RF signal chain, and it allows the receiver to be tuned across a wide band of interest, then translate the desired arbitrary received signal frequency to a known fixed frequency, thus allowing the signal to be efficiently processed and filtered and later demodulated. So once we actually pass it through the mixer, now we can put it into the lower frequency that we can actually work with and our more ideal circuits, our intermediate frequency ranges. And so once we achieve that, then these are the amplifiers that you may have seen in or amplifiers and filters you may have seen in ECE 100 and 102. And likewise, demodulation techniques, which you may have seen in 101. Finally, there's the auto amplifier, which we'll take a little bit of zoom in. And so this is some of the things that you might see in ECE 164. On the left side of the circuit in blue and in red, you see bias networks, whereas this right side is the actual amplification stage. And notice that the bias network is significantly larger than the actual amplification. That's because all your ideal voltage sources and ideal current sources don't actually exist. If you could make one of those, you'd be a billionaire. But the problem is that because these ideal components don't exist, we have to somehow make something that can achieve that same idea, which is that they will always yield that specific current or voltage. And so this bias network is actually how we achieve it. And the techniques to design something like this would be taught in 164. And so if you notice, there's a lot of techniques, or it all comes together. 166 covers the overall architecture and design. 164 is how you achieve individual components. And 165 would be something along the lines of your actual computer system, which is the digital logic. So the class is not, well, 163 is not listed here, but the required courses are 164, 165, and 166. They're offered in the fall, spring, and fall respectively. So 163 is actually offered in the spring as well. However, I would not recommend taking it together 165 just because they are so different. If you absolutely have no choice, then it's actually, you can't really help it. But in the past, 165 used to be offered in the winter, so it made a lot more sense to take a 163 later. But most importantly, 164 and 166 has historically always been offered together. Professor Rebez, who teaches 166, and Professor Hall, who teaches 164, work pretty diligently to make sure that your midterms don't ever line up too harshly and try to stagger your finals. So, they will try to make your life as easy as possible if you do take these two courses together. However, note that the workload is quite intense. I know that a lot of people in circuits do take these courses concurrently. However, there's a big penalty for doing so in that because 164 does have lots of homework and lab work, you will see your time getting stretched thin by that course alone. Plus a final project in that course obviously will be intrusive towards final study time. Then you have 166, which is extremely difficult. I would say might be the most difficult undergraduate course in the ECE department, possibly in all of UCSD. And so because of the amount of studying that goes into this course, I would say that it's advisable not to take these two courses together, but at the same time, you know, sometimes you have no choice, you have to do them at the same time. However, you'll find yourself with much more freedom to learn if you do take these courses separately. And so into the topic of job opportunities. So IC design is obviously highly relevant. Every bit of tech that we have, from our computers, our calculators, etc., has a chip in there that was designed by someone in a company. And so this is what IC your education actually builds towards. When you do design, when you go into industry, you'll be doing design work ideally. However, that's not all. That's very rarely the case for a starting engineer. If you graduate with your bachelor's, you'll find yourself having an extremely difficult time finding a job for design engineering, and you'll most likely be stuck with test engineer jobs. So it's highly advisable to seek a graduate degree if you're trying to go into design work. Note that the companies listed here, for analog IC, we have Analog Devices and Texas Instruments. Texas Instruments, as you might all know, is like the really popular calculator brand. And so, yeah, analog ICs, although they're not as prominent as long ago, they're still quite relevant. And one thing I actually discussed with my professors is that it's extremely difficult to get a job as an analog designer, but once you secure your job, you're pretty much irreplaceable. So there's that, you know, silver lining. If you do choose to go into analog IC, note that you will have to work quite hard to become the best of the field, because it is not quite as prominent as it used to be, and digital ICs have become far more ubiquitous. And so moving on to that topic, the notable companies listed here are Intel, Cisco, AMD. Obviously, there are plenty more, such as Qualcomm, etc. But we do still have, so Qualcomm is more so on the RF side, so sorry about that. But in the topic of digital ICs, this is where 165 becomes highly pertinent, and this is why ECE 25 is actually kind of relevant as well. So digital ICs are all your computer logic, the AND, OR, inverse, your NANDs, your NORs, etc. So all this logic put together becomes assembled on a tiny package of silicon and works together with other ICs to become your full computer or computational device. So if you do join one of these companies, then you'll have to get quite good at layout and stuff like that, which is taught somewhat here, but at the same time, I feel like one of the problems with UCSD is that it focuses too much on the math and theory, not so much on applications. You'll find yourself possibly needing a outside instruction, which is why internships are, you know, pretty important. And so moving on, we have for our board design, which is your PCBs and stuff like that, which is more general hardware-based CE, there are RF/analog boards for wireless applications. These are this is pretty much every company. You have anything with a modem, receiver, transceiver, etc. uses wireless signal. Anything that uses wireless technology will need RF and analog tech. And so this is where analog ICs are still relevant, but because of the fact that RF and analog are so hard to break into, it's one of those fields where if you can make it, you'll be irreplaceable, but you'll be struggling to actually make it that far. And then digital is the more ubiquitous field, which is also somewhat stagnating, but you know, that's like the problem with circuits. It's that there's this, it's limited currently by semiconductors. Until semiconductors makes a massive breakthrough, circuits have somewhat stagnated. And so you will be forced into a situation where you have to make a choice of, do I keep pushing through and become the top of the field, or do I settle for a job as a test engineer? So design work usually requires much more effort than testing, which is why in the job market, you'll find that test engineering is the most widely achievable position. However, if you stick with test engineering for too long, it'll be hard to move on to design. And if you can't move on to design, you can't really move on in the company, which is one of the problems and catch-22s of circuits. It's that if you want to break in, you have to be the best at the start. And so this is like probably the biggest issue with circuits, and which is one of the reasons why I moved on to machine learning. And so on to research. So our school is actually quite impressive when it comes to research within circuits. If you guys don't know, Professor Gabriel Rabais is pretty much a legend within the field. He's highly noted and worked on a lot of projects within RF. In fact, you'll actually see a lot of, papers citing his. In fact, as far as I know, Professor Rabais actually makes a lot of money for the school too. His lab is hugely funded. One of my friends actually got to work in his lab and said that his equipment alone probably costs more than like a large house. Anyways, so on the topic of analog devices, there's Professor Hall, who's sort of the head of that field, and he's quite notable as well. Then you have Professor Shui, who is one of the newer ones. I believe he's working on lower power devices. You have Professor Mercier, who does digital circuits. He's one of his projects that he boasted about in his class was that they worked on a digital IC that could be so small you could put it onto the back of a dead moth and pilot the moth. Obviously, the project was much more involved. It required the work of biological engineers and other chemical engineers, but at the same time, they were able to work together and design something that could actually be fit into the nervous system of a moth and pilot it to a limited extent, only to make it fly and turn. But at the same time, it's really cool that they actually achieved that. And yeah, so yeah, there's plenty of projects to work on for circuits in research. There's lots of lab work to be done. But the problem is that right now it's all limited to optimization. There's no room for massive breakthroughs because of our block wall of Moore's law. We are currently limited by the semiconductor devices, and so we are, until that has a major breakthrough, I don't see circuits going beyond just optimization at this point. Yeah. Any questions? No? Okay. All right. Shashank, I'll hand back control to you then.
All right. Thank you, Austin, for presenting circuit stuff.
Mhm.
So now we'll move on to photonics, which would be presented by Forrest. And Forrest is a TA here at UCSD who teaches for photonics. Let's see. Just give me a second. Looks like he's not online at the moment. Okay, I think we'll move on to the next depth because it looks like Forrest has trouble with his computer. So we'll come back again to this step.
Chuck, do I get Do I control or you control the slides?
Let me see. Okay, I gave you control right now. So
Okay.
let me tell Sam really quickly. Also,
Okay. Yeah, Sam's not here.
he's not online at the moment, so let me just message him really quickly.
Okay, yeah. Let me know when I should start.
Okay. Okay. Oh,
What just happened?
let me just. Oh, it's the first one. It's the first. Yeah.
This one. Okay. Sam is still offline.
He says he's gonna be joining soon.
Let me get my slides. Here. So machine learning. So machine learning, I think everybody knows this is everywhere. It's very popular. It's one of the hottest topic right now. So I think I don't need to introduce this to you guys. So at the core, machine learning is basically applied math plus computer science. So in order to be successful at machine learning, you have to be good at both. So here are some key math concepts or math area that you need mastery. So first is linear algebra. Linear algebra is very useful in manipulating. You learn how to manipulate matrix, how to put data into matrix form, and then manipulate data, and then get useful information out from data very easily. So linear algebra is a tool that helps you to manipulate and play with a huge chunk of data. So then later is probability, statistic, and calculus. So these 4 areas of mathematics are heavily used in machine learning. And then during the breadth and depth course, you will dive deep into the math side of things. And then, so these are the basic knowledge you need to know very well to do well in machine learning. So machine learning is a very broad field. So it consists of, so let me break it down for you. So it consists of a couple subfields that people often do research in. One is computer vision. So one of the problems that it would be considered to be computer vision will be image recognition. So you give a computer an image of Apple, and the computer, you want the computer to tell you Apple. So this application will be used in autonomous cars. So kind of like a speed sign recognition or stop sign recognition, or you want the car to pick it out with a stop sign rather than a speed limit sign. So you know when the car should stop. And also there will be robotic sensing. So this is also used widely in autonomous driving. So kind of they will use different sensors to fusion the data to give the autonomous car and robot a sense of what the world is like. It's kind of like our eyes and our ears, that kind of sensor measurement to get a sense of what surrounding is. And also machine learning is heavily used in data analysis. Kind of like, for instance, will be stock market prediction. So you want to predict what stock market is like tomorrow. So you can make best prediction and sales to help you make the most money. And then the other example would be kind of, you can feed in data to this model and to predict what is the death rate for COVID-19, sort of like how many people, what's the death rate made, and what should public official do to make the best decision to reduce death rate. So this kind of model building would also use a lot of machine learning techniques. So the other would be a very big one would be recommendation system. So when you go to Netflix, you see a lot of recommendation. You see a lot of movies that recommend to you, and then they will tell you this is something that you might like. So how do they figure out what you like? So they will take your data of your usage and then try and there's some models, there's some math go behind it and give you prediction of things that you are most likely to watch. And also there will be speech recognition, so things that go into the Siri or other types, Amazon Alexa, the kind of virtual assistants. So how do they understand what you say, right? Another field would be natural language processing. So this will kind of like a translation. So go to Google Translate. You can translate any language to English or and then vice versa. And then also search engine. So how does Google understand what you type into the search bar, right? So, and also with deep learning, I'll go into detail about deep learning later, but deep learning is basically a technique of machine learning that's widely used right now. So that's one of the most popular technique right now in both used in every field that you can see above. So in the control side of things, the control will be consider how to make a system stable. Something, for example, would be speed control, cruise control in your cars. You know, if you want your car to go 50 miles per hour, how to make sure it is going 50 miles per hour. Another types of control would be flight control you have in airplanes. So you know, airplane actually flies itself for most of the time during autopilot. So how to make airplane be stable? You know, there's turbulence and then other kind of varieties that happens in the air. But how do airplane respond to this kind of situation to make sure the ride is smooth as possible and as comfort for the passengers? So this will have a lot of discussion to system stability. The stability means system is stable even when there's disturbance outside, or even when there's influence outside, the system can still go back to be stable. Can I go to the next slide? So here are some classes. You would take I believe three depth classes, and then you choose one. You take these three are your required classes, and then you choose one among these three. So 171 is your linear control system. It actually overlaps a lot with 101. It actually overlaps a lot with the class taught by Professor Stephen Piper. So I think that's 103. I forgot the number. But you do learn how to analyze linear systems, and then love some stability theorem. So when you give your system, in what condition is this system stable? Or if I put some disturbance input here, and what should I do to make the system stable? Or what parameters I should adjust to make this system stable? ECE 100, yeah. There's some, and then so in ECE 5, you learn, you did PID control for the lane tracking car. So PID control, so go under linear control system. 171, you'll talk about that. And ECE 174 is your linear algebra class. So before ECE 174, the only linear algebra class you have ever taken is Math 20D, Math 18. But ECE 174 goes a lot in depth about linear algebra. It's a very hard class actually. You will need to spend a lot of time on this class. ECE 175, 75A teach about statistical learning, so some basic machine learning techniques. So this is kind of like the old-fashioned machine learning techniques, something like k-means or SVM. So this was the first time you learn about machine learning algorithms. So one of the projects you would do is and written digit recognition. So you feed in computers images of 1, 2, 3, 3. 171B is an extension of 171A. So you're going to do machine learning side of things. You can choose between 172A and 175B. I actually recommend 175B if you're interested in machine learning, because 175B, it doesn't say the titles here, but it actually teaches you probabilistic graphic model. So it's one of the very heavily used techniques and models in machine learning. In machine learning, actually a lot of times that people use graphic models to build models and make predictions. And the 175B will teach you the techniques and concepts of that. 172A, I haven't taken it myself, but from my friends, the lectures are not that, there's not a lot of material in lecture, but the homeworks for 172A are pretty good. So you can make your decisions based on what you want to do. So if you want to do robotics and intelligent system, maybe you want to go to 172A. If you want to do just machine learning side of things, you can do 175B. So here are some research areas. One research area is deep learning. Deep learning, most of the times people are actually concerned about architecture. So let me show you some example of deep learning. So here's ImageNet challenge. So it's one of the very popular challenge that people use to benchmark their algorithm in deep learning research field. So this is what the essence of the challenge is. There's like, I think, a couple millions, like 20 millions images, and then you want a computer to make prediction based on these images. There are 200,000 categories of images. So there's a lot of images, right? And then in 2000, so the bar here shows you the error rate. So you can see down the human is kind of about 5% error rate. So humans are 95% right, 95% of the time right. But in 2015, so ResNet actually achieved superhuman ability. So computers are able to recognize image better than human can do. So that's very, very impressive. So how do they do it? So this is how they do it. So they use something called convolution neural network. So more specifically, deep convolution deep CNN. So what I mean deep, what people usually call a deep neural network or deep learning is that these algorithms consist of a lot of computational layers. So for example, the AlexNet, so the one that has significant achievements in 2012 is one of the first deep learning algorithm that has significant accomplishments, significant breakthrough. So it has a lot of convolutional layers. So this is basically a computational layers. So data will come in, they will compute through layer 1, compute through layer 2. So basically it's a bunch of compositional functions. So this is your x, this is maybe your f of x. This is your g of f of x. This is your e of g of, you get the gist. So this is what people refer to as deep because there's a lot of computational layers in between. And usually what people find out is more layers you have. Actually, I can have laser here. More layers you have, the accurate result you have. So AlexNet here has 8 layers. And then if you see in 2015, the ResNet actually, I believe, has 128 layers, something like that. It had a couple hundred layers. So it's a significant amount of more layers compared to what original AlexNet had in 2012. So this is what machine learning is about, deep learning is about. And then there will also be data and mining analysis. So this will be concerned with how do you understand data. So there's so many data flowing around. How do you make useful information from these data? So computer vision, one example I talked about is autonomous cars, recognizing stop sign or speed limit or a traffic light. Or another application will be facial recognition. So if you have iPhone or any phone with facial unlock, how do the phone know it is you, not somebody else, right? And also it has natural language processing. This will be Siri for computer to understand human text and speeches. And also there will be hardware aspect. So before everything we talk about is software, but there's also hardware aspect of machine learning. So what you heard here about the people will say training on GPUs. So why do we want to train on GPUs? It turns out GPUs have a lot of cores. So for the best CPU you probably maximum have 8 cores. If you have 8-core CPU, that's one of the top of the line CPU money can buy. But for GPU, it turns out they have thousands of cores. Even for a mediocre GPU, you probably have 1,000 or a couple thousand cores, or even more. So more cores it has has more ability to do parallel processing, and this is very, very useful when you're training models. There's a lot of matrix multiplication, and so when you have a lot of cores, you can do these things in parallel, and then that will make this speed much faster. So there's a lot of research goes into how do you design hardware that's optimized for machine learning, both training and then inference. So Google has their own product, TPU, that's used in Google Cloud. Then Intel also has a neural network processor, and that's kind of like a USB stick you can pop into maybe to Raspberry Pi and then make the machine learning process training much faster. And also there's one more field of machine learning, it's called reinforcement learning. So this is rather new, but it has some very impressive result. So let me talk about AlphaGo. Maybe you have heard, but let me just give you an overview. So AlphaGo is the first computer Go algorithm that can beat human. So Go is ancient Chinese board games. The game is actually very simple. It's more you put the objective is to surround enemy pieces, and then you have you can put your pieces anywhere on the board. The board is quite large. It's much larger. I think it's 4 times larger than chessboard. And then it's very difficult for computers to solve. It's because there's so many possibilities. So unlike chess, if you're in chess, there are only a certain number of pieces you can move. And then each piece only has a certain number of moves according to the game of chess. But for the Go, you can take any pieces, you can drop it anywhere on the board. So there are so many possibilities. So people used to think it's very hard to solve Go because computers simply too computationally intensive. But Google, actually DeepMind, one of the subsidiary of Google, came up with the AlphaGo, the algorithm based on reinforcement learning. So this is the first application that has reinforcement that has great results. So AlphaGo, they use reinforcement learning that beat the world championship of Go. I think Lisodo, and also later beat the world championship of Go, Kejie. In later years, so no human right now in the world can beat AlphaGo. It's one of the best Go playing algorithms out there. And then how it works is that basically you tell computers, give computers some a reward function. So if it does something, basically it's like when you were young, your mom told you to study hard. And if you don't study hard, if you study hard, there will be reward. If you don't study hard, there will be punishment. So then later you learn you have to study hard and there's a good reward. So the same logic apply to the reinforcement learning. People actually build into this kind of reward and punishment system for computers. So you basically just let computer runs to have them figure out what to do. But if they do something that is add to the probability of winning games, you give them reward. If they do something that's hurt to the probability of winning games, you give them punishment. And then later the computer will learn what's the best strategy to do in order to win the game. So that's how they do it. But the math is quite complicated. So here I have some course recommendations that actually outside the depth courses that will help give you a better understanding of machine learning and then strengthen your techniques. So in CSE 154, you actually do learn about reinforcement learning. You do learn about the concepts of it. You don't necessarily learn how to program it, but you do learn a lot about, you learn how to program deep learning neural networks for sure. And then you learn about CNN, convolution neural network, so which is one of the most popular neural network for image recognitions. And then ECE 143 is programming for data science, data analysis. It's a Python class. So if you don't have Python experience, this class will be a really good introduction class for Python. And Python is very popular in machine learning and data analysis because Python is easy to use, easy to learn, and then there's a lot of good package and software out there. So most people who do machine learning research, they actually use Python, especially PyTorch, the PyTorch package, or TensorFlow. So these are two most popular machine learning framework that you hear people talk about a lot. So in ECE 154, you do learn about how to use PyTorch. And then in ECE 143, they give you a good foundation in Python, both the syntax of the language and also the like the idiom of the language. So you do become like a master in Python after 143. And also here, ECE 148 is another fun class. It's called autonomous driving. This is more on the application side of machine learning. So you're building an autonomous car that can drive alone drive autonomously on racetracks. So you don't necessarily learn how to write code in this class, but this class is more about the application. So you do learn how to train your model, how to fine tune your model, and then how to upload your training to the cloud to make the training faster. So UCSC actually has a GPU cluster. So we learn how to access the GPU cluster and then train your model remotely. So this is actually what people do nowadays. So they buy a GPU cluster from Google or from Amazon, and then because they have massive amount of resources, and then you can just train your model there. You'll be much faster than you would train locally on your machine or desktop. And then Sam will talk about the industry side of machine learning.
Hi, can you hear me?
Yes, I can hear you.
Okay. Okay, perfect. Yeah, okay. Hi, everyone. So my name is Sam. I'm an alum from UCSD, graduated last year. I did a BSMS in electrical engineering and machine learning at UCSD, and now I work at Qualcomm as a machine learning engineer in the multimedia R&D team, working on computer vision and XR related things. So today I'm going to cover some of the opportunities that you can commonly find nowadays at different companies in the industry. So first I'll cover sort of the different generic roles that you can find or get a job at different companies out there. So the first most common is probably a machine learning engineer. So that really entails of implementing and embedding ML solutions for different problems and applications that your particular company is trying to address. And also maybe design and optimize architecture based on certain specs and requirements. And for example, if your system requires a real-time latency or low power and so on, and all this really matter when you're building a real application. And most often ML models are very complex and compute heavy. So optimization is usually necessary. And it's very different from, let's say, like a project for your class, at school, because those requirements usually don't come up as a thing that you have to consider when you're going through assignments and stuff. And lastly, a lot of the times what ML engineer like myself would do is just writing a lot of code for different modules in the application, such as for your models. You got to build API, so sort of the pipeline around your module can use your ML models, right? Because you might be working in a team or with other teams for a particular product which they don't have the ML expertise. So you have to sort of think of it as like a bigger picture on a higher level and understanding the product and how you can design a ML solution that would be helpful to the product, because a lot of the times is the results is really what matters. You got to show that your ML solution performs better than like a traditional solutions. And a lot of the code are typically in Python most of the time. And then in the ML frameworks that we typically use is TensorFlow and PyTorch, and there are a few other ones, but TensorFlow and PyTorch are most common. Now, the second role that's also very common in even just companies or academia is as a researcher. So that entails tackling challenging problems, perhaps without existing solutions. They're really looking at really novel, challenging problems out there that no one has really solved or have a solution for yet. You could be pushing boundaries and improving state-of-the-art solutions. Or it could be conducting research mainly to publish conference papers or for your company's IP. So a third role
that's also very common is data scientists. So mainly you're responsible for any data related components in your application pipeline. And that sort of entails data curation or data pre or post processing, building a database for others to use, and so on. And perhaps also analyze data and report any meaningful findings. So the above is only a very general perspective, and it depends heavily on the company and the team's definition and needs. So for example, in a smaller team, a data scientist may even be responsible for all the things that a machine learning engineer would do. So it really depends on the company and the team. And I mean, you just have to probably read the description when you apply to the job, but just the names doesn't define what you do. The titles of the job doesn't define what you do, essentially. Can we go next slide?
Let me just give you remote
I'll just
access.
do it. Okay. Yeah, got it. Okay. So next I'm cover some of the companies and project areas out there. So on just a few logos out there, right? You can see the big tech giants like Google, Microsoft, Amazon, Facebook. I think mainly Google has a lot of research teams, and they have a lot of products out there that can take advantage of some of the features and performance that machine learning and AI can provide. And particularly interesting, maybe like Intel and NVIDIA, those companies will focus more on creating hardware for accelerating the different AI models for them to be used efficiently, maybe on mobile device, maybe VR headset and so on, or even like an automobile vehicle, right? And for maybe Amazon, they have A9, so they use a lot of AI in search engine, recommender system, customer analysis, and of course Tesla, Uber, they have the sort of self-driving cars, so autonomous driving, but also a perception of the surrounding, knowing where the pedestrian are, where they are locationally, and so on. And then maybe Salesforce that uses sort of AI into analysis into their product for the better features for their customers. And of course, Qualcomm, we've been spending a lot of resources investing in researching different areas beyond just mobile chips, because we're really expanding into different areas such as like automotive or XR and so on, and having research developing company IP and goes really well with licensing and so on. And we already have the hardware to support efficient hardware acceleration and very efficient on like edge devices and so on. And like BrainCorp, for example, they develop sort of cleaning robots, but that goes a lot into perception of the surrounding and creating like a map of the environment and sort of having a planning and so on. So that's a very active part of AI where you gotta make decisions and a lot of tracking and so on. And then of course IBM, I think we know a lot, we hear a lot about Watson since like a long time ago, being able to beat human in different games or just as a search engine, I suppose. And of course there are countless uprising startups that also sort of develop their products around using AI technology. So so I think that like now is really a big time for a lot of companies expanding using AI. So I think right now the job aspect is pretty good for AI related positions. And just I guess cover again the project areas. The main thing, as we really mentioned previously, is maybe e-commerce, recommended systems, and then computer vision, XR, and then autonomous systems, drones and robotics, and natural language processing, cloud computing, hardware acceleration, optimization, and also democratizing machine learning and open source. And that might sound a little confusing, but really that's just what TensorFlow and PyTorch are. They create a framework for people, the software developers, to be able to write code and design a model and to use the models, train models to use them. So there's a democratizing machine learning in a way. So that's all I have for today. Thanks.
Okay. So do you guys have any questions for Sam and Charlie?
Hello?
Oh,
Yes.
yeah.
Yeah, hi, Sam and Charlie. And I actually have two questions. And so first is like, as a machine learning engineer, like what courses did you take at UCSD that you find that's like the most helpful to your work? And the second question is, I don't know if you guys know, like, are there any like good courses that's relevant to like hardware acceleration and optimization? Thank you.
Okay. Yeah, so I guess I'll go first on that. So yeah, since I already did a BSNF, there are definitely a lot of the classes that I would recommend. But I guess just a good rule of thumb is the undergraduate classes is probably not enough for what a typical ML engineer is expected to do and know. So I think some of the courses like linear algebra, statistics, like those are the fundamentals are important, especially if you want to be a researcher. But maybe for a machine learning engineer, is not entirely essential to for someone to understand and know how to derive everything. So maybe if you read research papers, if you have enough knowledge to read the research papers for you to understand the different techniques or how to implement it into your application, then that's really what you need for the job. Like you don't have to be like a math genius or something. That's really for the researchers who are trying to push the forefront in different problems and applications. And for particular classes, I think generally like ECE 276, which is the robotics series. I remember that one is really good, and you can really just pick some classes based on your interest. So I know there's some classes in computer vision, like deep learning for computer vision, and you don't, and maybe like natural language processing, and you don't necessarily have to look just in the ECE department as well. Like you could look into the CSE department just to see what options you have. I think there's some classes in CSE department would complement pretty well with the ECE curriculum. Yeah, and I think another main thing is when you take those classes, make sure to have some of the classes in your curriculum to be hands-on in terms of the programming. So like Python, so you should be really good in Python, no matter which field of AI you're trying to go into, even as a researcher. Because nowadays research papers, they come with like a GitHub repo, some sort of code. So you really being comfortable and good at coding is very essential. And of course, any classes that you would do your assignments in TensorFlow or PyTorch, just make sure you be rigorous about those, because that's the framework you'll be using in industry mostly. So make sure you take your time in class. Take the opportunity to really be.
So yeah, Sam has an excellent answers. I want to add a little bit on that. So if you want to find a job, if your goal is the objective just to find a job, you actually don't need to know much of a math. You just need to know how to program. So if you are a solid programmer, you are for sure going to find a job. But the problem is, it's not going to last very long. So in order to move up, move up the corporate ladders, you actually become a maybe upper manager or something, or R&D scientist. You actually need to know a little bit more just than programming. And sometimes knowing how things work will help you to gain that kind of access. You don't necessarily just type in code every day, not knowing what you do. And then if you have some math background about like linear algebra, optimization, probability and statistics, that can actually help you a lot in your career, or maybe if you want to go into research in that aspect. So I think definitely you should know both theory and practice. And then one of the shortcomings of some ECE machine learning courses, they are more math oriented. So they actually don't teach you how to do programming. So if you go after undergrad with those ECE courses, I bet you will probably be a little bit difficult finding a good machine learning job, because they don't teach you much of programming, and then you just know a bunch of math. So you actually, I actually think you would need to know both, to be successful in both industry and research. So in the math aspect, I think ECE courses would prep you very well. And then if you wanted to pick up Python, I would highly recommend ECE 143. It's an excellent Python classes. And I think Professor Nguyen is suggesting there's one more ECE classes coming up, ECE 176, that should teach you more hands-on, more project-oriented programming. But I think definitely you want to pick up your Python skill before that, because most of machine learning projects or programming projects will use TensorFlow or PyTorch. Those are Python-based libraries. So before you take those classes, make sure you have your Python skill really solid. Like you want your Python to be like more than mediocre level. Like you want to be really, really good at Python. So that's what people, that would be a strong suit. Then also I would recommend CSE 154. So the only CSE classes you don't need any prereq. So I think that class is only need Math 20E, and then it's open to registration to other majors. I've taken that class. I think it's really helpful. That class actually teach you how to use PyTorch, and then you learn some basic deep learning, both techniques and then knowledge and practice.
Okay, that's very helpful. Thank you, guys.
Then if you want to learn about hardware acceleration, so there is actually one class open in the summer called ECE 180. So that's called CUDA programming. It's less about hardware, but it's more software oriented. But CUDA is what people use to program GPUs in order to make the parallel processing faster. If you train on GPUs, then people will tell you CUDA. What CUDA is. CUDA is basically programming. This is a set of programs that control GPUs and make sure that GPUs can run your machine learning algorithms.
Yeah, I also think that for even if you're an undergrad student, like I'm not saying that you have to get a master's, but maybe when you're at UCSD as an undergrad, you can take advantage of the grad classes, because no one is going to stop you from sitting in the class. Or some professors are even nice enough to provide you the resources like assignments, lectures that they use in that class. So like nothing is really stopping you from learning the materials from a grad class that is offered at UCSD. So if you're really passionate, right, maybe you don't want to spend another 1 or 2 years on masters, you could even just sort of audit the graduate courses that you're interested in, and maybe just learn from there. And there's really, and maybe it's even better to be less stressful. You don't have to worry about grade in a grad class, but just learning the materials. Or if you want to take it, that's fine too. But yeah, just wanted to add that.
Yeah, definitely take the opportunities that there are so many resources out here, and then you can fit in any class to learn knowledge if you want. And there are also a lot of online resources you can find. There is very decent virtual learning tutorial even you can find on YouTube or Coursera. So I think those would be a place to go if you want to find extra knowledge beyond classes.
Any more other questions?
And if there's no more questions, I will give control back to Shashank.
Right. Thank you so much, Sam and Charlie, for your time and presenting the ML depth. So right now we'll go to photonics, which we have skipped earlier. This will be presented by Forrest, who's a TA for a photonics class. So Forrest, are you there?
Hey, Sashan, can you hear me?
Yes.
Okay, great. Thank you. And thank you for inviting me. And sorry about earlier. My laptop decided that just then was the perfect time to crash.
Oh,
So,
no worries.
everything's up and running now. Again, thank you for having me. Hello, everyone. My name's Forrest. I'm a third-year PhD student studying photonics here at UCSD. I have been here since 2014. I did my undergrad here as well, then went to BSMS and now staying for PhD. The whole ride I did photonics the whole way through. And like Sashank said, I was also the TA for most of the classes for the last few years. So I'm going to talk to you today about the photonics depth and what you need and what you should do to prepare for it if you want to choose to go into photonics as in your future. So first off, what are the breadth classes that you need, or what are the prereqs for photonics? Photonics is probably the most physics-based depth in the ECE department. And from my experience as a TA, that tends to scare a lot of people because maybe people don't like physics, I don't know, but ECE 103 and 107 are the labeled prereqs for the photonics depth. And they definitely are necessary, especially 107, which is the electromagnetism course, E&M, because it is the study of light and how light interacts with matter, photonics that is. And you need to have a clear basis of, Maxwell's equations, which start off in ECE 107, and the wave equation in general. So it's definitely necessary. And 103, of course, that brings over all the semiconductor things. And we've already heard today from the devices depth that all the material parameters and material characterizations, et cetera, are kind of go hand in hand with photonics, because in the end of the day, although photonics is a very physics-y and physics-heavy depth, this is an engineering program. And so most of the photonics groups in the engineering program make devices. It's just they're optical devices or electro-optical devices. They're combinations using light, controlling light through electricity and heat and mechanical properties of different materials. Most of the time, those are semiconductors. So ECE 103 is also very important. One that isn't up there but through being a TA, I've realized is also important is ECE 101. I believe that's what it was, the linear systems class. And that's solely because that's where you start learning a lot of the Fourier transform things, Fourier series and Fourier transforms. And that's pretty important for a lot of the photonics classes because you're constantly going between wavelength and frequency domains. And that's just what the Fourier transform is. But as overall, I'm going to be ranting a lot today. Photonics is the study of light waves, and it has a huge field. It interacts with all of the fields. And can we go to the next slide?
You can control my screen, so you can just
okay.
move your keys.
Don't know if I can.
Okay, I'll just do it.
Sorry. Okay. So what are the classes that are in the photonics depth? There are the three main ones that if you're choosing to be photonics depth, you have to take are, it's all in the 180 series. It's physical optics or the bulk optics, then electromagnetics and waveguides, and then optical electronics, with which the devices depth already went over. And this kind of goes into this where we teach in the photonics is the different layers and regimes of photonics, because it all depend, how you treat light and how light interacts with matter depends on the scale of everything. And that dependence on the scale comes from the wavelength of light. So if you're dealing with devices that are, you know, a lot larger than the wavelength of light, which is typically hundreds of nanometers, it's going to be called bulk optics. So things like lenses and telescopes and microscopes, those are all huge compared to the wavelength of light. So you get to get away with a lot of classical physics and a lot of easier tricks and geometric physics to treat optics. Whereas when you get down to smaller and smaller devices like waveguides made out of semiconductor materials like silicon, or fiber optics like these micron wide pieces of glass that carry information around the world, you need to treat it with electromagnetic wave, because light is both a wave and a particle. So it all keeps going down into these different levels through the different photonics classes. Unfortunately, the deepest level you can go is quantum, so quantum optics, but we don't offer a quantum optics class because it's not required to take quantum physics in ECE. So I've heard from some of the optics professors that there might be a quantum optics class one day, but we'll see. That's neither here nor there. But optical electronics, or this 183 is probably the most photonics class of the depth, because photonics is the blend of electronics and optics. This is a very device heavy class. It goes over semiconductor lasers, LEDs, detectors, modulators, how they work physically and how you can model them using things like MATLAB. And then we also go into the lab and show you how to use them and how to properly, you know, measure them and characterize them. I will mention all of these classes, 181 through 185, they're all lab classes. So you will get a lot of hands-on training and learning in the photonics depth. Some of them are less lab heavy than others, like I'd say 184 and 185, these bottom two, that being holography and lasers and modulators, are more lab heavy than the previous three. But still, you will be constantly in the lab once a week or once every few weeks, learning how to connect fiber optic cables and how to set up laser systems and how to test a modulator, things of this nature. And they are very fun classes. It's a very cool experience. And who doesn't have fun playing with lasers? It's a lot of fun. So for 184, I actually have of these, I have the least amount of knowledge because one, I didn't take it and I didn't TA it. I TA'd all of these classes but 184. So I know that it has to do a lot with holography and Fourier optics. Again, 101 Fourier transforms crucial. But you do get to make things like learn what a hologram is and what isn't a hologram. A lot of things aren't holograms. And you get to make some, actually. It's pretty cool class. And then finally, lasers and modulators. This one, even though it's lasers is in the title for or the description for optical electronics, that only covers semiconductor lasers. There are lots of different lasers, like here it says CO2 lasers and Heine lasers, which are lasers made with gas and plasma. Then there's also amorphous gas or glass lasers and rare earth dope lasers. So you get to learn all the different types of lasers, how a laser works at all, and also tie it into modulators to make a system, like a whole system. Sure, the laser is just the source, but then what do you do with the output of the laser? How is it useful? Why was making lasers in the first place back in the 60s? Why has that pushed us to where we are now? So each of these classes is it's a lot of fun, for one, because they're all lab classes, and they're very informative. And they actually tie together a lot of the breadth courses that you've taken, that being 100 to 109, because you need a lot of these things. So next slide, please. Oh, and I guess one more note on the classes. I have known some of my students, they kind of jump around, even though that they are prereqs in the catalog, you can take them out of order, that being 181, 2, and 3. It will be harder, but it has been done. And the scheduling here, it's never the same every year. Like last quarter, 180. Well, actually, no, yeah, 181 was in winter. So I guess it is getting more correct. But then again, it's a 182 supposed to have a prereq of 181. Doesn't matter. Sorry.
Yeah.
So next slide, please. Okay, job opportunities. Photonics is applicable pretty much everywhere. It is a huge field. We're in the electrical engineering department, so most of our photonics groups deal with things like devices and telecom and imaging systems and some DSP, but you can pretty much get a job at any big company, like all defense companies, all aerospace and defense. They're always looking for photonics and optical engineers for things like, you know, sensors and detectors, modulators, material sciences. Like you have to know material to be in photonics. The CIMER was started by some people here at UCSD in the physics department, and they work with high energy lasers all the time, and like with lithography using deep UV stuff. And that's a lot of their things. It's a huge system, but it works with photonics. Intel, IBM, Google, etc. Apple, Facebook, Microsoft, the HoloLens, it's all photonics. But then that's all kind of sticking in the realm of electrical engineering. There's also a whole other side in medicine and biophotonics, like things like contactless probing and testing for characterizing different, let's say, viruses. If you don't want to get close to a sick person and test, you know, a sample, you can use light and laser light to do that with reflection and absorption spectrums. Then there's things like atomic clocks using photonic sensors. And then again, going back, there's also the data communication and telecom, like the things that I work in here at UCSD would fall under, I'd say, defense and telecom, where it's making these high-speed modulators to make information go through photonic circuits a lot faster. And then, of course, the big word nowadays is LiDAR. There's so many startups everywhere that want people in LiDAR, and so they need photonics and optical engineers to work on that LiDAR. So there's a lot of opportunities in photonics, and it's only going to get bigger and more needed in the next 10 to 20 years. Next slide, please. Okay, now as far as research areas, a lot of those job opportunities, they directly map to research areas here at UCSD and other schools everywhere, that being photonic integrated circuits. So what I work on, like I said, is small micro nanoscale devices for integrated circuits using optical wires, which are called waveguides, and making devices like being able to manipulate the light on these small circuits. Then there's also nonlinear materials and wave distorting materials and metamaterials and photonic crystals, and then small lasers like Professor, blanking on his name now, but there's a big group here that they do nanolasers. And then again, biophotonics, we have a big bioengineering group here as well, that there's probably a lot of collaborations there. And pretty much it's a lot of different research areas, and it kind of goes, like I said, it goes hand in hand with all the different job opportunities that are out there. So if you are a fan of materials and devices, or, you know, lasers and DSP and literally any of the things that I've just been talking about, photonics would be right for you. And next. Okay, I guess that's it. So if there are any questions, I'd be happy to answer any. Sorry for rambling a bit, but I'd be happy to clarify anything if anyone has questions. And if not, you can always just email me later. Okay. So sounds like no questions for now, at least.
All right.
Well, thank you so much, Sasheng, for having
All
me.
right, thank you so much, Forrest. Sorry to keep you waiting for so long.
No, no worries.
Okay, so next step would be signal and image processing, which would be presented by Yihan and Andy. So, just a second.
Mhm. Oh, now it says I'm controlling.
Hello?
Yes.
Yes. Okay. So I'm Andy, and I'm doing signal and image processing. So, what is signal and what is signal processing? I would say, this upper branch is more about math, and we are using different math methods and doing adjustments on signals. So, the most like the classes we took are more like a math class than engineering classes. Hello?
Hold on. Hello? Hello?
Yeah, Ihan, we can hear you.
All right, good. I was using two Zoom, so there's feedback. All right. So where should we start? Can you go back to the last slide?
This is just the overview.
Okay. Is it okay that I do on my screen? I think I want to write down. I want to write something, so it might be easier for me if I just broadcast. Or you guys like to keep it on your side?
I feel like it'll be smoother. It'll be like
Okay. Okay, sounds good.
I think you can annotate it. I gave you permission to control my screen.
Oh, hold on. How do you go back? Oh, I'm on an iPad. I'm sorry.
Oh, sorry.
Okay.
Okay. Yeah.
All right. So DSP.
So Andy already gave the introduction, so we're on this.
Okay. I'm sorry. All right. So applications of DSP, right? You can ranges from as low as low level machines, such as it can code on a DSP processor, or you can go as high as use applying deep learning on learning different transfer functions and filtering techniques. So one thing that's very common and very popular in the DSP domain, or in the entire SIP depth, is audio processing. So you can see this pretty much every day. So when you go to a rave, when the DJ is turning the knobs, they are essentially applying, for example, low pass filter or band pass filter, high pass filters to create those cool effects. And there's also a lot going into sound design. For example, one of the coolest headphones that we have on the market right now is that can deliver as real, like as spatial as real audio to the listeners, such that you will feel like you're in a you're you know, like in a very vivid concert where you're having a very cool live experience, and that's also part of the 3D audio. So as much as image and video processing, you see that not only in digital cameras, image restoration, you also see that in computer vision. I think so. When people are trying to identify objects, they're also applying filtering techniques in those implementation. And the third major topic or area in DSP is communication. 5G, for example, is a very, very hot topic right now. People are trying to come up with ways to deliver those very high frequency, very strong signals without interfering with other common signals that, for example, like airline signals where phone signals, where I'm sorry, airline signals where what else out there? But yeah, I mean, I think the part of communication for that part just different transmitting techniques, and yeah, and then how to interpret data efficiently. As far as for machine learning, there's a lot I think that's covered in the previous depth, and then how DSP can be applied is that it can tell you the statistics of a particular signal by applying different methods, by applying different machine learning methods, and then DSP is also used in face and audio recognition together with machine learning. But yeah, I think that's as far as I can think of right now. In terms of control systems, I think that goes more into the low level. For example, like chips design. How do you design chips such that it can handle the very high processing speed that's required for DSP calculation. So let me get the next slide. All right, so I think it'd be cool to show you guys some examples. So one cool lab that's actually on campus is called Sonic Arts. What they do specifically is to design ways to deliver audio, to deliver spatial audio, to be more specific. And another cool thing that they do is they actually design a beamforming speaker that's already commercialized, and first patented and then commercialized. So think about the situation where you have 3 listeners in a room, and then they're standing in different locations, say ABC, and then you only have one speaker in the room, but somehow by applying different beamforming techniques, which is a part of the huge DSP family, the speaker is able to deliver 3 different audio tracks in 3 different languages, and they can deliver those sound to those listeners in ABC locations simultaneously without overlapping. So if I can click the link. Right, so I think this is their page of their research. The technique, how do I scroll down? Yeah, can you scroll down just a bit? Just a bit on the top, the first one, the sound beaming, the first one. Right, so this is a speaker that they designed. It is the more technical term is called sound beaming. So So one of the cool things that they do is that, well, one of the cool implementations of the speaker you can think of is that if you install a bunch of these in a museum, then you can have a bunch of people from all around the world, and they can deliver explanation to your specific art piece in multiple languages, and they're all listening to it at the same time, and they can all understand it at the same time. And another thing that I think that's pretty cool from this lab, if you just scroll down a little bit, is the space. Yeah, it's a space 3D. So they calculate the impulse response, which means how room reacts to sound when you, for example, when you clap in a room. They come up with different ways to simulate the path of refraction of the sound in the room, and that they can create multiple reflection, and then you will feel like you're fully immersed in the audio. All right, so let's go back to the slide. Right, and the second example is that we use is from Professor Mohan Trivedi. He is the guru in computer vision. He developed a lot of cool facial recognition techniques that's applied in cars, and not just facial, but like different kinds of computer vision recognition techniques. And the last one, I believe, is the auto effects, which is you can see this a lot in those production videos. I'm sure you have seen those cool music production videos where they just apply a track and then they apply this phaser, filtering, a bunch of other stuff, and all those are actually they are all developed with DSP algorithms. All right, next slide. So I think Andy will cover this.
Yeah. So besides the classes in the PowerPoints, we still have ECE 45. Like in my opinion, that class is the foundation of every single class on the slides. So if you're gonna take DSP as your upper division, make sure you get an A in ECE 45, because in that class you will learn the foundation of everything basically. You will learn the Fourier series and transforms and convolution, which you will use that as a technique in every single classes. So besides ECE 45, another very important class is ECE 101. So ECE 101 is basically the another ECE 45, but harder. And in that class, you will basically relearn everything in ECE 45 and learn other like sampling series and stability series. And you will also learn poles and zeros. What is poles and zeros, which you will use in ECE 161B. And for ECE 109 and ECE 153, so those two classes are the probability series. It's very useful if you learn it, but those two classes are not that relevant to the major classes like ECE 161 series. For ECE 161, we have ECE 161 A, B, C, and for ECE 161A, basically you are going to do review for ECE 45 and ECE 101 again. That's the reason why ECE 45 and 101 is so important. And plus, you will learn like to build the finite impulse response filter and infinite impulse response filter. So basically, ECE 161A is more about filters. And for 161B, you will learn the math behind different filters so that you will have a better understanding of the like what is the math behind the filters. And for 1C, we are going to do applications using the filters. So 1C is more about coding. I would say like the coding skills we use in 1C is basically like the addition, like the summary of every single class before. Yeah, that's it for the class.
All right. So in terms of job opportunities, all of those major companies like Google, Facebook, Apple, they're all doing DSP related work. For example, how they deliver better sound using just speakers from phones and from devices like phones and as big as MacBook. And then you can find DSP being implemented together with machine learning these days, because deep learning, machine learning, they're the biggest trend in the world right now. There's always better way to improve the closed form techniques that were developed from before. And then if you want to go specific into audio, then Dolby, Universal Studio, Disney, Yamaha, or SoundHound. These are some of the very nice companies that they're hiring DSP people every year. And then actually Qualcomm is also doing some awesome audio work. They have an audio research team there that that delivers audio audio components on devices. So in terms of communication, there's some local companies like Hughes, Cisco, and Vicet, and for circuits, Qualcomm, they cover everything, and then one of the companies that I like to visit our campus very often is Maximum Integrated. So yeah, so in general, there are lots of companies that are around that are they're constantly looking for DSP people. And then I just want to add that DSP is not just about audio, images, machine learning. They're also about probability and statistics. So if you for example take DSP as your depth, and then you also very good at probability, you can probably think about becoming a data scientist as well. And then those are very popular positions at all the companies, because big data, it's a world of big data. All right, so I think that summarized the depth for DSP.
All right. So thank you, Yihan and Andy.
Of course.
So next we're going to move on to computer systems design. Should be presented by Ashley and Curtis.
Yeah, hey, I'm Ashley, and I'm a graduating senior in electrical engineering. Obviously, my depth is computer systems design, and I've pretty much taken classes all over the board with different depths for my technical electives because I could not decide. And so computer systems design definitely felt like something that was more my speed. And so I feel like computer systems gives you a nice computer science foundation that I've seen come in handy many times, both as an engineer and as a project manager. Being an electrical engineer with some C++ knowledge kind of makes you a prized melon at the career fairs, but beyond that, it gives you a much deeper knowledge of how the technology around you works, which I think can come in handy even if you do something only tangentially related. So I feel like we kind of broke this down into two branches. It doesn't have two official branches. You can take any of these classes and mix and match them. But I feel like it kind of has two different themes, software engineering and computer engineering. If you want to work on the front end or back back end of websites, as a computer engineer on FPGAs, processor design, or circuits, then the more computer engineering classes may be what you're looking for. So stuff like 102, 103, 165, and 111, which are required to take at some point to fulfill either one of the 5 depth courses, your design requirement, or as a tech elective. I feel like the computer system design depth gives you a good enough foundation to apply to entry-level software engineering jobs. And if you go the extra mile, the jobs you're eligible for really open up. If you practice and do some projects outside of class and go through Cracking the Coding interview, which is a really helpful book, you'll definitely be in pretty good shape to apply to related jobs after graduation. See, I don't know how to control this. How do I go to the next slide?
Oh, isn't it? Okay, let me just go to the next slide.
Sure, thank you. Curtis, do you want to talk about 16?
Oh yeah, sure. So yeah, ECE 16, it's kind of it's a project class. So the way it works is that there's labs, and you start small by like getting LED to blink on Arduino, and then you end up with this like heartbeat sensor that gets fed into your computer, and that you can like graph your heartbeat and all that cool stuff. So it mostly involves like, you know, like Arduino, microcontroller, Python, and in general, it's a good intro to embedded systems.
Yeah, and then ECE 17 is similar to like CSE 11 if you've taken that, or 8A and 8B, but works with C++ instead of Java. This class was pretty intensive, but the professor for this class is really good at helping you grow your skills, and after you've taken it, you'll have a much better idea of object-oriented programming. And then if we go to the next slide. So 102 is kind of like 100 if you've already taken that. It's a lot of like active filter design. It includes a lot of time spent in the lab working on physical circuits and simulations of your circuit. And honestly, this is probably the hardest class I've ever taken, but you will learn a lot.
Yeah, and 103 is it's kind of like basically a crash course in nanoengineering. And it's like a useful class if you want to get into like chip design at the silicon level. I think these two were kind of like talked about previously, so they're the same class, but these can also count as your depth classes. Sorry, there's like a huge plane in the background. Yeah, so you can, for your depth, you can choose any of these 5 classes. You don't have to do all of them or any of them in particular. And then 111 is, it's a system Verilog project class. So if you really enjoyed like the ECE 25 labs and wanted to actually learn Verilog properly, then I would highly recommend this class. You basically learn how to use like Altera or Vivado, depending on the professor, and then you build and simulate like a and it's also pretty laid back. And the reason it's for the asterisk is like, as Ashley said, this can count towards either your depth, your technical electives, your professional electives, or your design class. So it's pretty flexible, but you do have to take it for this depth.
Yeah, and so the 140 series, these classes cover a lot, everything from product and project management, IoT, and, to web development will be covered. The labs in 140A are really interesting, and you build and train a neural network to direct a little robot car to follow a line or avoid obstacles. In 140B, you break off into teams and develop a project from the ideation stage all the way to the release of your product. Through this process, you'll not only learn more of the technical skills involved, but also the product development side of things, which will definitely help you relate to others when you work in a cross-functional team. 140A and B is a data structures and algorithms class and focuses a lot on the design of code. It really extends what you learned in ECE 17. So if you liked that class, then you'll definitely like the 141 series. In 141A, you'll do a lot of the smaller coding challenges, and in 141B, you'll build a database from scratch, including your own query language.
And 143, the machine learning dev also explained this pretty well, but it's basically a crash course in Python with a focus in data science. And the thing I would like to add is chances are if you think you know Python and you take this, you will probably learn more. You basically learn like all the main Python modules and do like a data science project at the end. And then 158A is, it's basically intro to networking theory. So you learn about a lot about like the math and algorithms that are kind of like the main driving force of the internet. And then 158B is a continuation of that, but it's a lot more software based, and most of the homeworks are like actually programming assignments. And you learn a lot about all the modern internet protocols like HTTP or like BitTorrent or DNS and all the stuff that drives like the modern internet. And you also learn how to like sniff network traffic with Wireshark, which I think is pretty cool. Makes you look like a hacker.
Yeah, I absolutely loved 158A. It is basically like a bunch of fun math tricks. 165, I actually haven't taken this, and neither is Curtis, but this class will involve some of the same stuff from ECE 25, except here you'll be designing those logic gates from transistors. Austin explained this class much better earlier, so I'll just leave it at his description so I don't mislead anybody.
Yeah, next slide. Yeah. Okay, so this is a slide I made like a few minutes before this, but these are some recommendations for electives. You don't have to take these, but in my opinion, these pair really well. So for other defs, if you do like 172A, it's a really good kind of intro into like computer vision. And that class also has a lot of programming assignments. So like it pairs really well, you get an edge. And then 159A as communications dev, it's another communication class, but information theory and coding is also really important if you want to get into like kind of network design. And then the thing I really enjoy about computer systems is that you can actually fit like an entire depth into electives because it's so flexible. You have a lot of electives. And so personally, what I'm doing is I fit the entire machine learning depth into my electives. Yeah, so for project courses, a lot of these courses have already been described, but 148A, I mean, not 148A, 148. It's like you build an autonomous car project, pretty cool. 196 is another project class where you pick like, it's kind of like a prototyping class. So it's like similar to 16, but if you like doing things again, like more projects, then this will be fun. And then 180 is, there's a 180 class that's about GPU programming that's only offered sometimes, but this is also kind of fits really well with like computer engineering. And CSE 145, I haven't taken this class, but I know a lot of people who did, who were also EE, and it's pretty great because this is one of the few CS classes that you can actually, you don't need prereqs. You can just fill out a Google form and the instructor, and that's pretty much it for this slide. So for job opportunities, as like you might get the impression that this is a really good intro to like software engineering. So a lot of things that you would traditionally expect like computer science or computer engineering major to do, you can also do with this dev. And so like you expect like all your big like software tech companies to be a good match. And then in terms of job roles, like we kind of like said, there's two ways you can really go with this. So pretty much anything on the board from like software engineering, firmware engineering is a big one, full stack, and like if you want to go into computer engineering, then digital design, FPGA engineering would be like what you would be going for. Yeah, that's pretty much it here. And then same thing for research, really. Like a lot of the traditional like computer science, computer engineering roles, you can also like fit into with this dev. And so there's a like interesting like kind of buzzwordy stuff like Internet of Things, artificial intelligence. yeah.
Yeah, there's also like a lot of really interesting research going on at San Diego companies, so I think you're in a good place to be. I mean, Qualcomm is right next door, and then Medtronic up in Carlsbad is doing some really interesting stuff with ventilators. So if you have a strong math background, you can take your research here really far and do some really interesting things like working on robotics or networking. Yeah, so I think that's pretty much it, unless Curtis has anything else to add. If you have any questions, definitely shoot them our way.
I mean, I didn't really do a lot of research, but I guess I can like talk about myself in conclusion. So I really wanted, back when I was a freshman, I really wanted to switch into computer engineering. And then all of a sudden this depth came out, and then my GPA was too low to switch into computer engineering anyways. So like picking this depth kind of, it was like, it basically saved me from depression. And I also did a lot of like CSE courses, like the main lower div ones. And I would say compared to like the CSE department, our equivalent courses in software engineering are, they have arguably better instruction because like the staff to student ratio is much higher because these classes are a lot smaller. And also like the software classes, they're all taught by professionals and not like tenured researchers as in the CSE department. So like they really know, they're really like up to date and know what they're doing. And then I would say like, yeah, this is a pretty good like kind of alternative CS major. Like how, I don't know if you guys know, but there's a trend of people who can't get into CS doing things like data science or like cog sci machine learning. And I would say it's kind of like that, but it's more low key and people haven't really discovered it yet. And yeah, that's all I have to say, I guess.
All right, so I'd like to add something. So Professor Nguyen actually mentioned that if you take the computer systems design depth, you can actually petition for CE major if you decide to do BSMS, which is something you can't do as an EE major. You have to, usually you have to be a CE major to get into the CE BSMS. So just something to point out. All right, so thanks a lot, Curtis and Ashley, for presenting the computer systems design depth.
Yeah, so I can talk a little bit about power. Can you guys hear me good?
Yep.
Okay, cool. So for power engineering, you sort of have a couple of different focuses. The main thing that sort of drew me to power engineering was transformers are kind of something you don't use and like in our normal EC classes, but they're all over the place in power engineering, and I wanted to learn more about those. So a couple things that you do in power engineering that aren't in other ECE depths are transformers, three-phase systems, and stuff like that. You deal a lot with rectification and converting DC to AC, DC to DC. If you want to like step up a DC voltage into another DC voltage, you can use a buck. If you want to step it down, you can use a boost. If you want to do both, you can do a buck boost. You delve a lot into those converters. Obviously, if you want to change into DC to AC, you use an inverter to easily switch back and forth from a sort of constant waveform into a sinusoidal waveform, and we delve a lot into that in our classes. So you start off here, hit the next slide so I can talk about those classes specifically, more specifically.
All right.
Sweet. Yeah, so for 121, that's sort of your basic fundamentals. So you learn a lot about your transformers, how to analyze the systems you're going to be dealing with in future classes. You deal with a little bit of three-phase. You're sort of introduced into it if you don't know what that is. Essentially, our grid runs on three-phase, and you can transfer power more efficiently with a three-phase source than a one-phase source. So you get some benefits there, and you sort of learn the basics of that, which you're going to apply to your future classes. 121B delves further into the transformer physics itself, the inductors, the windings, the flux through the windings, all of that stuff is covered in 121B. In 125A, you mainly focus on AC to DC converters and DC to DC converters. So you sort of get your feet wet with that class and then go on to 125B, where you sort of take what you learned in 125A and you build a project to build a solar panel system. So essentially you're designing a whole system to get power from a solar system, a solar panel, and then send it through to the grid. So a solar panel, if you don't know, will take in DC energy. So you're gonna have to convert that to the AC before you send it into your grid. So that's sort of the basic classes. Some other classes that aren't mentioned here are the 128 series. I haven't taken A or B, which I'm planning to do in fall and winter, but I've taken 128C, which deals with power grid resiliency. So it's sort of two main focuses in the power engineering depth. It's the 121 and 125, which focus more on the power electronics side of things, and the 128 that focus more on the power system and the grid sort of things. So for 128C, you delve into the power grid and how it's affected by weather conditions. And it's a really fun class because you learn how heat waves, droughts, wildfires, lightning strikes, tsunamis, monsoons, ice, all of that stuff, how they play into affecting the grid and affecting the efficiency of the grid, and how to sort of circumvent some of those problems that arise depending on the certain weather conditions. And another class that's not mentioned here, but is worth noting, is ECE 124. And what 124 focuses on is motor drives. So essentially kind of the same thing, except now you're also dealing with mechanical components as well. So when you're converting from DC to AC, essentially you want something to be spinning, causing torque, stuff like that. So that's covered in 124 if that interests you. That's and the project that you focus on in ECE 124 is actually doing a wind turbine system. So you basically model the speed of the turbine, be able to control the speed of the turbine, control the torque of the turbine, depending on what you want to do. And you sort of model that whole system as well. Next slide.
Are you able to control my screen? I gave you permission.
Nope. Oh, it worked. We're good. Cool. So some job opportunities that I've learned through taking the classes with professors. Actually, Abi Samra, he has his own power company, and he gives out recommendations, heads up, if you're a good student in his class and talk to him about different power grid stuff. He is the professor for the 128 series. On the other hand, the 121 series and 125 series is led by Reza Ismaili, and Reza Ismaili is actually part of Solar Turbines. So if you want to know more about that sort of stuff, those are a couple of job opportunities from professors at our university. Other ones is General Atomics. I talked to a previous alumni from UCSD about power systems on naval ships. So that's something that you could do as well. I don't know too much about Siemens, but I know that utility companies definitely are a big one, especially in different areas of research, and the obvious sort of electric vehicles, and that sort of relates more to ECE 124. So if you potentially want to work on electric vehicles, I would recommend taking ECE 124. It's a pretty fun class. You learn a lot and you do a lot of hands-on experience, and I'll show you guys a schematic from 125B a little later on. Next slide. Oh, is it gonna work? Cool. So some research areas that you can get into are microgrids, so essentially smaller sort of independent grids that work together to sort of create a larger grid. And then distributed generation, don't know too much about that, but I would assume that you're distributing the power generated from substations and stuff like that. Smart grids, this is actually a big one for Abi Samra. He sometimes teaches a class on smart grids over summer sometimes, so look out for that. He sort of tells you the benefits and why smart grids are sort of the future, because you have a system that's constantly able to take in data. you can pinpoint exactly where problems start occurring, and you can sort of predict where future problems might occur, and you can sort of take in all that information and sort of automate it. Because currently, to know where a transformer fails is pretty difficult. You'd have to sort of triangulate it, and that takes time and a lot of resources. So a smart grid definitely has some benefits there. You can also work on voltage regulation between two systems. You can work more on the DC to DC conversion that I was talking about, using buck converters, boost converters, buck boost converters, choke converters. All of those basically just step up the voltage in DC, step down the voltage in DC, or do both potentially. Some other things that you might be able to do is switch regulators, solar panels, pretty much any renewable energy source has some aspect of power engineering in it that you can sort of focus on. And in 124 and ECE 125B, you sort of focus on solar power and wind power. So that's two of the big ones. And in 128C, you sort of overview all of them just because different weather conditions will affect different systems in a different way. Such as if you have a drought, hydropower is takes the biggest toll in terms of efficiency. And especially with different regulations being put in place, hydropower sort of takes a big hit there with the different sort of cooling systems. So there's definitely a lot of research available to sort of figure out new ways to do things or focus on existing things like line insulation coordination, which is essentially when lightning hits a tower, then you can basically you sort of detect where faults would occur and sort of design the system so that it doesn't create a fault. And that sort of deals a little bit with, what are they called? Traveling waves like 107, just because you have to see how the waves and voltage and current waves are going to propagate throughout your whole system. So that's sort of, you learn more about that in 128C. So like I said, you can work on some motor drives. I don't have my example of my wind turbine system that I'm currently creating, in the process of creating, but I do have my solar panel system that is in the midst of being created right now. If I can share my screen. Can I share my screen, just Sashank?
Yeah, let me stop sharing my screen really quick.
Sounds good.
All right.
Cool. Yeah, so, yep. So this is sort of the start of my system for making a solar panel. Right now, you obviously can't see the solar panel in action, but this is sort of the focus of 125B. Essentially, this voltage source would act like the solar panel. So once I'm done modeling it and testing it out, then I replace this voltage source with a solar panel. And then on the other side, this is sort of where the grid would go. And essentially, I'm not completely done with it because these three actually need to get sent to a control system, and also these three, all of that gets sent to a control system to basically regulate the voltage at the input side and the output side based on these voltage probes. But essentially what's happening is you have signals that are getting timed using this three-phase source, and essentially these three signals get here to both of these. And what this does is this is a diode rectifier. So essentially it rectifies your signal and basically chooses the maximums and mins, because you want to send those max and mins back to this sort of system. That way you get rid of some of the harmonics that end up arising when you're doing some power engineering stuff. Because if you didn't know, if you have harmonics into your system, you lose efficiency and you potentially are losing out on more energy that can be used. So we have this sort of system in place to regulate a couple of the harmonics, specifically the third ones and any larger ones. The sort of control system takes care of that. And then you're also going to have what we call a DQO transform, which essentially takes the ABC sort of normal 3 phases that you have and actually turns them so that one of them is basically not visible to the system, to simplify the system down from 3 phases back down to 2 phases, which is a little bit easier to deal with. And then once you're done with that, then you transform it back. So this is still in the process, but this gives you sort of an idea of what you do in some of the power engineering courses, specifically working on control systems, working on AC to DC converters, which this H bridge is basically. And yeah, and then you have this resistor and inductor, the resistor to model the losses in the system, the inductor to act as a current filter. I still need to put in capacitors for a power factor correction and for sort of voltage, like a voltage filter. Therefore, when you get to the grid, it's actually a clean 208 line to line. So yeah, that's all I have to show you guys from a current working project that I'm doing. I can talk more about that in the Q&A if you guys are interested. So Sean, can I get the slides back?
Sure. Just a second.
Yeah. Yeah. So that's sort of my solar panel system currently. And you can work more on the sort of, it's not just power engineering. I think it's a lot more of systems once you get to the higher operatives. So definitely if that's something that interests you, you could look into that. Oh, I went too far. Let's go back. There we go. And stuff like a laptop charger has the other aspect. So we have the grid sort of power system, and this is more power electronics. So all the stuff that goes into things like laptop chargers, the transformers, the power factor correction capacitors, all of that stuff, it leads back to power electronics. So essentially you have your rectifier to make sure your signals are how you want them. You have capacitors and inductors to filter out voltage and current. You have power factor correction, and that's because in a 3-phase source, you might not have a load that actually matches itself. So you sort of match up the loads with the power factor correction and sort of make sure that you're outputting active power instead of reactive power. Therefore, you can actually use it. Because essentially, if you're using reactive power, if you're producing reactive power, I should say, then you're losing out on efficiency because that's sort of power you can't really use. So all the stuff that goes into this, like diodes, you focus a lot on diodes in your circuits to make sure that current's traveling the right direction, and you sort of deal with different components that you don't deal with in other classes like thyristors and other things like that. That's pretty much it for me. Cool. Yeah.
Oh, so does anyone have any questions for Alan on power depth?
Cool.
All right, thank you so much, Alan, for presenting power depth. Okay, so you also have the option to make your own depth. So the only thing is that you got to make sure it follows a logical order in terms of what ECE classes you're taking. And you also have to, you might want to check with the ECE department once, just to make sure they'll approve of it. And this way, if any of these depths aren't really what you're looking for, you want something more specific, or you want to take more specific classes, this would be a really good idea. And some helpful tips. It's okay if you choose the wrong depth or you want to go into one depth and you decide to switch, because whatever depth you're currently taking, you could have that count as your technical elective or professional elective and then switch to a different depth later. So it's not like it goes to waste. And also having the technical electives and professional electives are a really good opportunity to explore different kinds of depths. So like a lot of speakers, you could actually go into multiple depths using this. And also, like I mentioned before in the beginning, make sure you might want to check all the prerequisites to the course, to all the courses that you'd want to take, because there are a lot of prerequisites that are only offered once or twice a year. And these could be potential obstacles if you don't really plan out well in advance. So definitely make sure you satisfied all the prerequisites and make sure you got them in order so that you'll be able to take the required classes as soon as possible. And also, you also have the option to do the BSMS program where you can receive a master's degree in just one more year. And as you've heard of in a lot of depths, they require a master's degree makes you a lot more valuable in the industry and will give you opportunities to the core design related jobs. And the fact that the BSMS program is set up really straightforward, I think it's a really good deal. Also, some helpful tips just to keep in mind is that there are a lot of ECE classes that use MATLAB for stuff like projects and you'd also use it in research and industry. So it'll be really good to get comfortable with MATLAB just because it'll be used a lot in the upper division courses. And also coding is a really big skill that you'd need to learn. Especially if you're something like ML, where you're eventually going to be doing coding almost exclusively. But yeah, just really get familiar with all the classes and your professors, all the courses that they teach. And to get industry experience, of course, always try to get internships. And then if you guys are, you want to go more into depth of what we've discussed about, you can always use these links to get a better idea of what is required for all the courses and everything. And thank you all for coming. Thank you to all the speakers and everyone that attended. I hope this helped you and gave you a little more clarity on all the depths and what you'd want to do in the future. So now, like before we get into the breakout rooms, I'd like to have Keshav on the line. So just give me a second on that. Hello, Keshav, it's Shashank. Sure.
Hello,
Yes.
can you hear me?
Yes.
Okay. Thank you all, everyone, for coming to the event. Just some last minute things that I wanted to kind of go over, which was kind of spread out through the entire event, but primarily the ECE department over the last couple of years has been really switching over to a hands-on curriculum. And so they're adding a lot of hands-on classes like 16, 17, 140, 141, 144, 148, and so on. And they cover like a huge range of things. And in addition to this, another student organization in the ECE department called ECE USC are doing a different sort of event where they have faculty coming in and talking about how you apply these different depths in careers and giving you a more career focused perspective. And I think Professor Nguyen sort of wants to give you a little bit more brief on that. So I'll let Professor Nguyen come in and talk a little bit more about that. Professor Nguyen.
Can you hear me?
Yes, Professor.
Okay, great. So thank you for a great workshop, and I like to thank all the speakers. As Keshav said, this particular workshop talk about classes and the perspective of a student that went through the curriculum and so on. Another organization, the Undergraduate Student Council. Hello? Can you hear me?
Oh, yes, Professor.
Okay. Another organization is focused on the career advice. If you're taking particular depth, what kind of career do you have, and so on and so forth. So we will be announcing those videos later on. I'd like to just give a summary of the perspective of the department. So we design the depth and give the student a lot of elective courses, right? So as we said before, do not focus on one areas. Try to take courses in different areas. For example, if you have courses in signal and communications, you open up yourself to a lot more opportunity for internship in communication systems. Signal processing is also very important for machine learning. Machine learning right now, all the model is training on very clean data, meaning the data that they give you in a database or being clean, curated, and so on and so forth. But before that, you have to know signal processing to be able to filter the noise, process the signal, and so on and so forth, right? Photonic and circuit, high-speed circuit that interfacing photonics with chips, very important area. Power management, power electronics for circuit, and so on. So I think having background different area also help. One other thing I wanted to touch on is BSMS program. Right now, if you are into BSMS program, you are a very strong student. And it's likely that you already have a tutor position in the department. As a tutor, if you're taking MS courses or if you are an MS student, as a tutor, we will pay for your tuition fee, and also we'll give you a stipend as well. So having accepted into BSMS, having a tutor or TA position, you're more or less getting your your MS degree for free. Okay, so that's the power of BSMS program here. But excellent workshop, and I can hang around for questions. Thank you.
Everyone, I've stopped the recording, and Shashank, I'm making you the admin now.